Hello, everyone. Hi. My name is Shayan Durudi, and if you don't know me yet, I'm one of the TAs of the course. And I will be teaching the next 3 lectures. And we're going to do basically a 3-lecture sort of mini series on AI and education. So these lectures will mostly be focused on applications of AI, in particular to education. And we will be seeing some new sort of AI topics as we go along. But a lot of it's going to rely on things we've already seen before. So first, let me give an overview of what the next 3 lectures are going to cover. So it's going to be, as I mentioned, a series of applications of AI to education. And then I sort of chose 3 different sort of aspects of education for the 3 different lectures. So today's lecture, we're going to talk about applications to learning. And here I mean human learning, not machine learning. But we're going to use machine learning for human learning. So it can be confusing sometimes. But so these are applications of how to model human learning. And then for Wednesday's lecture is going to be on assessment. So testing students and things like that. So how AI has been applied to assessment. And the last lecture will be on instruction. And so these are sort of high-level applications. We're going to talk about very specific, particular things. And the machine learning techniques, the AI topics that are going to be involved in these. For today's lecture, we're going to talk about machine learning and a little bit of search. So these are things you've already seen before. On Wednesday, we're going to talk about application of machine learning and mechanism design, which is sort of an application of game theory for assessment. And then the last lecture, we're going to introduce a new topic, a new machine learning topic called multi-armed bandits, which you may have heard of. And it's important to note that education is a very big space, and we're not touching upon a lot of things that are considered education. For example, educational policy, systems of schools and classrooms and things like that. There may well be applications of AI to those areas of education, but what we're looking at here is more sort of at the cognitive level. So like if you think about it, it's a very sort of low level. It's what's happening inside the student's mind and trying to sort of measure that and try to improve education at that level. So it's mostly about cognition, learning, and instruction, rather than more high-level aspects of education. So before we actually go into these topics, I'm going to briefly talk about the history of, so that's what we're talking about today. But I'm going to briefly talk about sort of the history of AI in education, in particular at CMU. So I think this is sort of an interesting, brief, discussion of how these 2 areas, AI and education, have been integrated at CMU. And I think it has actually a pretty interesting sort of history of how they co-evolved and why actually this topic, if you're not aware, is actually a big focus of research, especially in the HCI department and the psychology department at CMU. And so one of the main goals of these lectures is so you see a concrete sort of application area of how AI can be applied. That you haven't seen before, and hopefully it will get some of you interested in this topic. And if you're interested in how you might be able to do some research on this, I'm happy to talk to any of you. What some open questions are in this area. Okay, so as I think was mentioned in the first lecture, in 1956 there was a Dartmouth workshop in AI, and this is just a snippet from the proposal of that workshop. It was proposed, I believe, by primarily John McCarthy, I think, at Dartmouth, and so this is what it says. It says, the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. An attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. So improving themselves is sort of like machine learning. We think that a significant advance can be made in one or more of these problems if a carefully selected group of scientists work on it together for a summer. They might have made some advances in the summer, but this is still basically the goal of AI, although it's taken different directions over the past few decades. So this was from the 1950s, and as was mentioned in the first lecture, 2 of the participants of this workshop or conference were Herb Simon and Alan Newell. And they were professors at CMU. At the time, they were in the Graduate School of Industrial Administration, I think, which is now Tepper School of Business. And so they continued this line of work for the rest of their lives. And the interesting thing is that if you look back at this description, it sort of focuses on how they're trying to mimic intelligence. I mean, this is obviously what AI is, but mimicking intelligence that's on humans. And I think Herb Simon and Alan Newell sort of exemplify the kind of work where they simultaneously worked on AI and cognitive science, cognitive psychology. Whereas nowadays, a lot of us, working on AI aren't really focused on the cognitive aspects. Of course, there's neural networks, but that's pretty far removed from how, learning and cognition happens in the brain, even though it's motivated from that. But they really were focused on how humans do cognition and then trying to use that to make systems, intelligent systems that can do things similar to humans. So like Herb Simon, for example, studied, actually both of them studied humans working on problem solving tasks, like the Tower of Hanoi problem, and coming up with like cognitive rules. And Alan Newell, based on some of that work, actually developed the SOAR model of human cognition at CMU. And then a few years later, John Anderson joined CMU in 1978, and he's currently also at CMU. He's in the psychology department. Herb Simon and Alan Newell both passed away. I think Herb Simon passed away in 2001. Alan Newell passed away in the 90s. John Anderson was sort of motivated by the work done by Alan Newell, so he joined CMU, and he developed another theory of human cognition, which is the ACT-R theory of cognition. And so why is all of this relevant? Well, they're modeling human cognition, and then John Anderson and another researcher who's also at CMU, Albert Corbett, they developed what's called the Lisp Intelligent Tutoring System in 1983. And this is one of the first of a class of work called Intelligent Tutoring Systems, and that's actually a big focus of work in the HCI department, even to this day at CMU. So basically, actually, it's an interesting story. If you read his biography on his website, he says how he started working on intelligent tutoring systems to come up with a way to break his theory of cognition to try to improve it. Because he sort of came up with a model called ACT-STAR, which he thought was sort of like the final version of his model, but he still didn't want to retire, so he's like, well, there's probably something missing. So what if we apply this to try to instruct students, and in doing so, we're going to find problems with this model. He did that, and he actually developed an intelligent tutoring system that was actually very successful in teaching students. And that developed a whole sort of legacy of work on these intelligent tutoring systems. And I guess he was less successful in trying to break his model, but later on, I think that came about, and he improved this model. So sort of, it was not made directly because he was necessarily. I mean, I don't know if he wasn't interested in it, but it wasn't because he wanted to work on education per se, but he wanted to better understand human cognition and see how his model would work in the real world in instructing students. So what was this? This Lisp Intelligent Tutoring System was basically some software that teaches Lisp, which is a programming language. And it's actually a programming language that's sort of central to AI, which shows that he's among these AI researchers, to students. And they got really good results on this. And so this tutoring system uses some form of AI. Now, the kind of AI that it uses is pretty, nowadays we might not think it's super intelligent. Part of this is actually using his theory of cognition to develop rules for how a student might respond to problems. And it's sort of like a series of if-then statements. They're called like production rules. So that's a form of intelligence. What should you do if a student does a certain thing, and then you can branch based on that. But it's more intelligent if you think about it because it's motivated based on understanding how humans think. So it's different from the kinds of AI that we use today, but it is definitely, because it's motivated by cognitive science, you can think of it as a form of AI. Although their tutoring system later on also used another level of AI, which was sort of student modeling, which we're going to touch upon in this course, in this lecture. And I'll talk more about that briefly later. Later on, more researchers joined this endeavor of working on cognitive science and also intelligent tutoring systems. And then Carnegie Learning was founded in 1998, including two CMU professors. The co-founders were two CMU professors, John Anderson and Ken Kittinger, who's also in the HCI department currently. And this has taught math, algebra, and I think pre-algebra to over 500,000 students. So they're making real live impact. And if you look, I really believe this history goes back, again, to the history of AI. So the history of AI is sort of at CMU, as it developed, sort of co-developed with this sort of work on cognitive science, and it led to actual instructional systems that have taught millions of students. So I think that's really fascinating, personally. And actually, maybe what's a little less known is Herb Simon directly was actually very interested in education and not just the cognitive aspect of things. And here's just a sample of papers he's published with co-authors on education. So I don't think you can see at the very top, it says what we know about learning. And he has this sort of quote about how the state of learning, like there used to be some schools where students were copying what the instructor was saying and taking notes really fast, and he's saying some schools still do this. And he's basically sort of saying the state of education is sort of lacking, and he's giving suggestions for how to improve it using AI. But he also emphasizes that he doesn't completely view it as a sort of computational problem, but he actually advocates for having learning engineers at universities that sort of design better learning environments and improve the work they do. And I think part of his interest in this was actually also as an instructor himself, not just as a researcher. So those two things combined in him. And so just to give you one other, let's see, this works. Yeah. So there's actually recently, I don't know if you've heard, but there's something called the Simon Initiative at CMU. And of course, this is named after Herb Simon. And this is sort of, actually, I guess we can go to what is Simon here. So I don't know if it releases what it is. But it says the initiative's goal is to measurably improve student learning outcomes, and both at CMU and more broadly. So it's about basically organizing everyone at CMU doing research on student learning and instruction, and also giving grants to instructors who want to improve their education. And this was motivated by a lot of the things that Herb Simon was talking about decades earlier. And so this sort of actually goes over a lot of the things I mentioned. This is a timeline, and it's labeled Reinventing Education Based on Data and What Works since 1955. So again, it's motivating what I just said, which is that this work on developing better instructional technologies using data and using AI started in some sense since 1955, which is pretty cool. And there's a lot of applications here mentioned. So I went over a lot of these, but there's some interesting things here. Some things aren't really relevant. They just probably want to fill up the timeline. Simon wins a Nobel Prize in economics, but that's not really directly relevant to this. But one interesting thing here was that, I don't know where it is, but there's something about the, somewhere here. Anyways, it was about the Panopto system, which is what's currently being used to record our lecture. So that was developed at CMU as well. So there's a lot of work on developing better educational technologies from CMU. So that was sort of just a brief, discussion of this sort of history of AI in education, how they're sort of intricately related. And actually, I was just checking the HCI faculty web pages, and I counted, I think, 11 out of the 33 faculty members there are actually at some level working on education and instructional technology. So that shows that how much that this is sort of core to CMU. And I think, unfortunately, a lot of people don't realize this because we don't have a school of education. And a lot of our focus on education, again, is at this sort of cognitive level and developing educational technologies, which at a school of education, you'd find lots of more qualitative work and more work at the systems level, studying schools and classrooms. Whereas at CMU has a very different focus. But hopefully I've motivated that there's a lot of interesting research happening at CMU. So now we'll go into actually some of the things that is happening at CMU in education in the next few lectures. Especially in this lecture, a lot of things I'm talking about was sort of developed at CMU. Yeah, so now we'll start with our applications of AI to learning. Again, human learning. OK, so here I'm showing an example of what's often called the learning curve, which you might have heard of before. And in this particular case, it's called the power law of practice. So this is basically a curve. On the y-axis, you have error rate. So this might be students working on some task. And this plots the error rate versus on the x-axis, you have the opportunity to apply some rule or some problem that you're working on. So basically, the x-axis is showing how many opportunities a student has had to practice something, and the y-axis is showing the error rate. And it shows that the error rate declines as a function of the number of opportunities the student has had, which makes sense. But in particular, it's saying that the error rate declines in a power law. And you might not be able to tell this from the plot unless you do a lot of math, or some math at least. But a power law basically is, just go here. A power law is a function basically that here P is performance. So performance can either be error rate, as shown here, or it could be reaction time. So how long a student takes to do a task. So maybe they can do some task perfectly, but it might take a longer, short amount of time. And as they practice the task more, they can do it more quickly as they go along. And you probably notice this yourself in different tasks that you do. So it maps some measure of performance to basically how many opportunities it takes. And that the number of opportunities is raised to some power b. So this is a basic power law. You can generalize this by adding more constants. A and b here are constants, and you can fit this to data. So if we have data, for example, here, this might be for a single student, but if we have data from many students, we can fit a power law of this form to find the constants a and b. So this is a very simple sort of application of machine learning. And actually, usually power laws are often they're seen in this sort of log-log form where you take the log of both sides, so you get that the log of p is equal to b times the log of t plus the log of a. So in this form, it's sort of a linear relationship between the log of the number of opportunities to the log of the performance, whether that's the error rate or the reaction time. So Newell, Alan Newell, again, so we're going back to these people, and Rosenblum, another researcher, they wanted to test fits of various models, including a power law, to learning curves, and they found that the power law best fits a variety of different, let's say, learning tasks, or practice tasks where students are practicing something. And not just students. I believe some of these were maybe factory workers doing certain tasks. Basically, anything that they got their data on, they tested. And they found that the power law does explain these curves best. Now, the interesting thing is that there was sort of, and maybe even still, there's a debate in the literature if that's the case. Because at the time, apparently this power law practice was sort of well known at the time that Newell and Rosenblum were working on this. But especially they said in cognitive psychology, researchers were sort of ignoring that, and they were saying no, that learning learning curves fit an exponential curve, which is interesting. So that they want to test this. So what they did was, you might not be able to see, but here are basically a bunch of data sets that they found, and they fit an exponential curve, a hyperbolic curve, and a power law to each of these, and they found, probably can't see, but in almost all of these cases. In a lot of these cases, the R squared, so the correlation coefficient, is very high, like over 0.9. In some cases, like 0.99 or 0.98, regardless of what model you fit. Which is interesting, because that means even if you fit an exponential curve, you're going to find maybe a really high correlation. So you would expect an exponential curve really fits the data well. But they show sort of as a trend, actually, that the correlation coefficient for the power law is at least a little bit higher, I think in every case maybe, or almost every case. So that seemed like convincing evidence. But the interesting thing that they did was they did an analysis where they fit the curves, and they sort of visually looked at how well the curves fit the data, rather than just relying on this correlation coefficient. And they found that the power law consistently sort of models, I think, one of the tails of the curves better than either of these other models. I thought this is interesting because it's sort of, when we do machine learning, we don't typically do this kind of analysis where we're actually thinking about looking at the curves and because sometimes when we find a model that fits data well, we'll just say, okay, that's good enough, and we'll go with that. But here they're very particularly interested in what model fits the data best, because it's actually, they're trying to model how students learn, and they're interested in the cognitive aspect of things. And this sort of, I think, really sort of exemplifies the kind of work done at CMU, where they're not just trying to do, in the past 50 years, where they're not just doing some sort of machine learning or statistics, but they're really interested in coming up with a theory of cognition. And they're using this as a tool to help them develop that theory. So I find that really fascinating. And they actually give sort of they came up with an explanation for why a power law makes sense using a cognitive theory. So once they saw that the data sort of says a power law makes sense, once the data showed that power laws fit these different data sets really well, they tried to say, well, what kind of cognitive theory would help us explain this phenomenon? And they came up with something, at least. But interestingly, another set of researchers in 2000 gave an alternative explanation for what's going on. And they said that each student's practice is actually better fit by an exponential curve. So in all of these data sets, we have data from many different students, and we're trying to fit sort of a curve to data from all of the students simultaneously. And they're saying if you actually took each student's data individually, so in that case, it would be similar to the curve I showed you earlier, where each opportunity just has one point. And an exponential curve would fit that data better. And they give sort of a justification for why aggregating these, the data fits a power law better. So this is actually particularly interesting. And they have this paper, which, I don't know how strong this evidence is myself, but the paper was called "The Power Law is Repealed" or something. So they're really attacking this law. But this is particularly important because it's saying, we might be able to come up with a model that fits our data well. But if we want to later use this model, and I'm going to show some applications of this, if we want to use this model to try to understand how students learn, or to try to trace how students are learning while they're doing a certain task, if we're using sort of a power law, whereas an exponential fit is better, we might be making wrong conclusions, and that might affect, however we're using a model. If we're using a model to somehow improve instruction for students or to, understand how well they're learning materials, then it actually makes a pretty big difference. So, just whatever model fits our data best isn't necessarily the full story. It actually might be important to understand why, and also, again, in this particular case, maybe to see if, a model that fits our data in aggregate might not be the same model that fits data for individual students best. So now I'm going to move on to sort of how do we use these kind of models to inform, to actually try to model student learning. So these power laws, or if we're using an exponential curve, are sort of a simple explanation of a phenomenon, right? It's saying that you just look at how many opportunities a student has had to practice something, and then you relate that with what their error rate is on that task. But there's a few other complexities that might exist when we're trying to model a student's learning, let's say, in an intelligent tutoring system, or in any learning environment, maybe even in a classroom, although we want to have data for how students are doing in the task, like at a sort of granular level. So if we want to do this, there's a few things we have to consider. One is that there may be individual differences in students, right? So certain students might learn faster than others, or certain students might have prior knowledge, right? So we can't just use the same learning curve necessarily to fit all students simultaneously, right? So we might want to fit different curves for each individual student. Second, students might learn different skills at different rates. So I mean, in the aggregate, students as a whole, certain skills are easier and certain skills are harder, right? So for example, addition, one-digit addition, for example, is easier than two-digit addition, which might be easier than multiplication, for example. So we don't want to fit the same curve to all tasks, right? So if we have an intelligent tutoring system, let's say, that's teaching many different skills, we don't want to fit one curve and assume that students are learning all skills at the same rate. That's a pretty bad assumption. And finally, different problems may actually share some of the same skills. And I'll show an example of this in a second. So how we actually are going to model this, we're going to fit a parameter for the ability of each student. So student I is going to have a parameter theta sub I. And for each skill k, we're going to have a parameter beta sub k. And then we're going to have something called a Q matrix, which is going to map each problem to a set of skills. So let's look at an example of a Q matrix. So here on the rows of this matrix are items, and where items are sort of problems. So for example, any problem of the form A times B, so any multiplication problem might be a particular item, and then a multiplication problem where we have an addition after that might be another problem, and so on. So then we look for each item, what are the skills involved in doing that? So for the first problem, the only skill involved is, actually, this is incorrect. Can anyone notice the error here? Hopefully. OK, yeah. It should be multiplication. So we should have a 1 in multiplication and a 0 for division. OK, sorry about that. So for the second problem, we have an addition skill and a multiplication skill. For the third problem, addition and subtraction. No, sorry, multiplication and subtraction. And lastly, we have addition and multiplication. So what's one thing you notice about in this matrix? Just anything interesting? OK, maybe it's not very interesting. But OK, so these two skills here, these two items have the same skills, right? Now, are they the same problem? Are they the same type of problem? Yeah? Who thinks they are? Who thinks they're not? OK, there's a few hands for both. I think more people thought they are. Well, is 2 times 4 the same type of problem as 6 times 8? Because here we're modeling them as the same, right? We're saying A times B. Any problem of the form A times B is the same. Is it the same? What about like 1,000 times 40? Yeah. Oh, you're saying they are the same? They're different. Why are they different? That's an excellent point. We're going to come back to that. Yeah, so in this case, that's a very good point. The second one tests order of operation. So if you do C plus A first, you're going to get the problem wrong. But you don't have that problem as long as you're working from left to right, which we do. So I mean, there might be weird edge cases. But one general principle here is that what differentiates two different types of problems is sort of not very clear necessarily, right? It requires maybe some expert knowledge of the task. And this kind of expert knowledge is work that a lot of these people at CMU, for example, Herb Simon, Alan Newell, and John Anderson, they were interested in these things. How do you develop an expert knowledge of this task? And what they would do is having like experts work on a task or novices work on a task and sort of find out what rules they're applying in different tasks. And these rules can then be used in an intelligent tutoring system to differentiate between different types of problems and different types of skills. But yeah, so we're going to come back to this point that these two problems might actually require different skills. But you can even imagine that a problem of the form a times b, if those numbers are very big, that might be a different skill, maybe from 1 digit to 2 digit. Or even as a better case, what about factoring numbers? If you're factoring numbers up to 100, that's not very hard. But if you're factoring very big numbers, that's quite hard. So you don't want to model those as the same skill. So you need definitely some amount of expertise to develop these skills. But later we're going to show how AI combined with expertise can actually help develop what's called a cognitive model or a Q matrix like this, or help improve a Q matrix. OK, so let's go back to this. So we have this Q matrix which maps each type of problem to a set of skills. And there might be some overlap. Like in this case, we're modeling, these two problems probably wouldn't have different rows if they're being modeled with the same skills. We'd probably just put them together. But I differentiated them because we might actually want to separate them out. OK, and we're gonna call the probability that a student I answers a question J or an item J correctly at opportunity T, we're going to label by P sub ij T. OK, so now we're going to look at a model to try to predict how sort of the error rate of students as the number of opportunities increases. So in this model, we have we're going to map the logarithm of the probability that the student answers a question correctly over 1 minus the probability the student answers a question correctly to this quantity here. First, let's think about what the left-hand side is indicating. This is what's typically called the log odds. So the thing in the log is sort of the odds of a student answering a question correctly. The probability of success divided by the probability of failure. So it's sort of the odds that a student would answer correctly. And then we take the log of that. And we're mapping this to theta sub I. So what was theta sub I? Just make sure you remember.
Yeah, the ability of students.
Right, the ability of student I. And then this sum here. So what the sum is saying is we're summing over all skills, k, and we're taking the entry of the Q matrix corresponding to item j. So remember, we're trying to predict if a student will answer item j correctly. So we take the entry in the Q matrix corresponding to the cell with the row of item j and the column of skill k. So if this is a 0, we're basically not going to include that skill, right? So if we're looking at like the problem a times b, then we're going to sum over the division skill, but we're just going to ignore it because it has a 0 in the matrix. Otherwise, we include it in our sum. That's all that this is doing. We could have alternatively written the sum over k in the set of skills for item j. This is just a different notation. And then we sum beta sub k, which is sort of an intercept for that skill k. So you can think of beta sub k as the difficulty of the skill. So different quantities of beta will differentiate between easier and harder skills. And then we have gamma sub k, and gamma is sort of the learn rate for that skill, times t, the number of opportunities. So as the student sees more opportunities, they have a higher chance of answering the question correctly, as indicated by gamma. Does that make sense? Any questions about this? OK, I have a question about this. So we have a poll. So the poll is asking, which of the following is true about this model? So the options, I'm going to release it soon. The options are, it is a linear regression model. It is a logistic regression model. It follows a power law of practice where P, remember our measure of performance is going to be the log odds, right? Rather than P being the error rate or reaction time, we're going to look at the log odds of the student answering correctly. Or it follows an exponential law of practice for P being the log odds. And this is going to be possibly have multiple correct answers. So let me go. So the poll is released. Let me go back to the slides. Oops. All right, so let's look at the answers. So about every answer has quite a few votes. The most common is that it's a logistic regression model, which is good. That is true. It is a logistic regression model. It's so who thinks it's a linear regression model? Who still thinks it is? Nobody? I mean, A lot of people thought it was. Did everyone change their mind when I said it's a logistic regression model? Nobody wants to advocate for being linear. Yeah.
Evaluate Pij in terms of P. You have
Say it louder.
if you just take exponential both sides, take Pij, the form comes up to be the same 1 minus exponent.
So you're saying it's a logistic regression? Yeah, but does anyone want to advocate for being a linear regression? No? No. I mean, a lot of people voted for it. Yeah.
If you just classify the left-hand side as y, and then these qjk's and things as x's, then this is just y is the sum of
Right. That's right. Yeah. So actually, as written here, it is a linear regression where you're classifying, or not classifying, but you're regressing this. This is your y, the log of your odds, right? So there's sort of a trick question because it's both a logistic and a linear regression. Yeah.
I think it would be true if you said it is a linear regression for p equals.
Yeah, I didn't say that, but so yeah, I purposely left that out just to make it a little trickier. I mean, either way, I can see justification for either answer. I mean, any logistic regression you can transform to linear regression where you just change your the y basically. So that was sort of the trick there. So just to show that there's a transformation. Does anyone want to see how to get it into the form of a logistic regression? Or is it clear? I think most of you voted for that, but I can show the derivation. Basically, you exponentiate both sides, and then you can derive it. But if anyone wants, we can derive it on the board. Okay. So for the next two, let's see what you guys said. So more people thought it follows a power law practice than an exponential law. So does anyone want to say why it follows a power law practice? No? Who voted for power law? Probably people who thought I've been talking about power law, so it must be a power law. Does anyone want to say why it's an exponential law of practice? I didn't actually give an equation for exponential law, but hopefully you could have come up with what that might be. Anyone? Yeah.
take an exponential on both sides, and then the log disappears, and you get an exponential on the right side.
Right. Exactly. Yeah. If you take if you x both sides, you get you basically just get an exponential of this. So that does correspond to an exponential law of practice. If you think about the simplest case, where you ignore the theta and the beta and stuff, you're just going to get an exponent of gamma times t. So it doesn't follow a power law practice. But how could we modify this so it would follow a power law practice?
Actually, I have a question. So
Yeah.
for it to be an exponential law, would we need p to not equal log of the ratio, or would we need p to just equal the ratio?
Oh, right. That's true. Sorry about that. Yeah, so that's wrong. Yeah, so I guess it probably follows neither. So yeah, you would need p to equal just the ratio, not the log of the ratio. Sorry, that was my mistake. Good point. Very good point. Okay, but assuming we were saying p equals the ratio of the odds, how would you change this to make it follow a power law practice? If you can make one simple change to the equation. Someone said something.
Remove the log.
Remove the log? And what happens if you remove the log? Sort of you just get a linear relationship, right? Between opportunity and the opportunity and the odds, right? So that wouldn't be a power law, it would just be a linear relationship. So what is a power law? How would we model in terms of, yeah?
Do we need a log over the sum?
Log over the sum. So log outside of here? Yeah, so you could do that. That's sort of weird. It's not weird, but it's because then you're taking the log of these parameters you're trying to fit. So I guess what you probably want to do is take a log of the number of opportunities. Right? So you take a log of t. So if this was log t instead of t, it would follow power law. So if we ignore all the terms except for this sort of gamma t, then we have that the log of P, right, or performance, sorry for the, that was wrong, is going to be equal to sort of the log of, sorry, gamma, some parameter times the log of t. So we have, again, that log relationship. It's linear when you take the log of both sides. Does that make sense? So as is, this doesn't follow power law. And this model, I should have said somewhere on the slides, but this model was actually sort of proposed by some researchers at CMU, Ken Kettinger in HCII, and Brian Junker in the stats department, and one of their students. And I don't know why exactly it doesn't follow power law necessarily, but they actually motivated it by saying with the power law practice, but in the end it didn't follow power law. So it's a little bit tricky. You might not be the first ones to be confused about this, but you could do either. Again, I think the story is still not clear about whether a power law or an exponential law better model student learning. And if you remember, what I said was that it seems like perhaps an exponential law better fits a single student's learning rather than when you fit the data as aggregate. So it might be better to model student learning using an exponential law rather than a power law. But I think it's still sort of an open question, or at least to me it is. And there's been work on using a log or not using a log. So either doing power law or an exponential law. OK, so are there any questions on this? Are there any questions about the model, what the different parameters in the model means? OK, another question, how would you, so I said that this models, we want the models to sort of differentiate between different students, right? So how would you be able to even more differentiate between different students in a sort of natural way? So what does this model say about different students? Let's start with that. What parameter in the model affected? Yeah.
Like the kind of intercept, if you think of log odds of y, is different. And so they start at a different spot, essentially.
Right. So different students basically starting out, before we teach them anything, before they do any practice, they start out in different spots as far as what's the probability they're going to get something correct. In terms of log odds, but I mean, obviously it means they're going to have a different probability of getting the question correct starting out, right? Each student might have a different probability. So how else could we modify it to differentiate even more for different students? I actually mentioned it when I was talking about different students.
Different students learn at different rates.
Right, exactly. So how would you incorporate that into this model?
You
Sorry.
change beta ki, where it's a function of that particular student.
Change the beta?
So beta is the learning rate, right?
Theta or beta?
Beta.
Beta, no. Beta is the intercept for the problem. So beta sort of corresponds to the difficulty of that particular skill.
Yeah, but the learning rate between students could be different, right?
Potentially, yeah. So I'm saying, how would you incorporate that into this model? Because that's not currently in the model. Students are assumed to learn at the same rate. So in particular, students are assumed to learn at a rate of gamma for skill k. Yeah.
I was going to say, isn't it gamma that's learning rate, not beta?
Yeah, gamma is a learning rate, but it's fixed. It's the same for all students. It just varies for skills.
Add an I subscript.
OK, so you can have a gamma sub ik potentially. That's one way of doing it, yeah. Or you can have a separate gamma sub I. So maybe you have like a separate learning rate. There's different ways of doing it, but that's a reasonable way. So why might you not want to do that, though? Why do you think this model chose not to model students at learning at different rates?
I mean, we will have so many parameters that it's basically saying that we take each particular student and feed the model to that particular student, then another model to another student, etc.
Right. Yeah, so you'd have a ton of parameters. Basically, you need a lot of data from each particular student in order to fit this model. Especially imagine you have lots of skills. If you have like 100 skills, then for each student, you're going to have like 101 separate parameters. Even having a separate parameter for each student here is sort of already difficult to fit, because you can only use data from a particular student to fit this parameter, right? You can't use data from other students to fit that particular parameter. So imagine if you have a different separate learning rate for each skill and student, that's going to be a lot of parameters. So basically, it's a way to avoid overfitting, right? It doesn't mean that we necessarily think students all learn at the same rate. Maybe there is reason to believe that, and that would go back to what our cognitive theory might say. But we don't want to do that if we don't have a lot of data. Or even if we do, we probably don't have enough data to model that accurately. Even this theta I, in practice, it's actually fit a bit differently, where you fit sort of a mean theta parameter, and then you just look at the different potential theta parameters to fit sort of a variance around that. Because, for example, assume you want to use this later to predict the learning of a particular student. You don't know what that theta parameter is for a new student, right? A student you've never seen before, you don't know what their ability is, unless you somehow measured it elsewhere. So this theta parameter is already a little bit difficult to work with when you're trying to see how new students learn, unless you can measure their ability somehow. So if you sort of model, like let's say you have a normal distribution around thetas, and you fit sort of the best normal distribution over student abilities, then that gives you sort of a more Bayesian way of working with when you see a new student, you know what distribution might be sampled from, but you don't necessarily know their ability. And then you can sort of update their ability as you go along in a Bayesian way. So let's think about how concretely, let's just make sure we understand this. How would you actually, if you're trying to fit this, let's say in Python or something, how would you actually model this as a logistic regression? Because the way it's written, it's not necessarily clear, right? Because let's say we have a different parameter here for each student. So sorry, I guess that should be more concrete. Let's say we want to fit a single logistic regression model. We don't want to fit a different model for each student, right? Because there's sort of data, we can sort of share different parameters, right? Because we sort of want to simultaneously fit a student ability for each student while fitting these skill-based parameters for each skill. And we want to fit these simultaneously. So we don't want to split our data set for each student and then fit separate parameters, right? So how would we fit this using a single logistic regression model? So basically, what would our set of features be in the model?
You could add a feature that tells you which student it is, possibly.
Right. So you can have basically sort of a dummy feature that tells you which student it is. So and whenever you have a new student, you're only selecting theta I. All the other thetas will be zeroed out because you have a 0 for those features. So you'll have basically the number of features you have, again, is going to be a lot in this model. So again, if you have if a separate learning rate for each student, then you're going to have many features. And then, yeah, I think that covers it, basically. OK, so is that clear? OK, so if we're going to ask you to fit this on the homework, which we won't because you already got your last homework, you know how you would do it? OK, cool. OK, so how is this model used in practice? So I'm going to show one way that this can be used. So there's a website here called DataShop. So DataShop at CMU, I guess. So this is basically a large repository with, I think, over 1,000 sort of data sets of, from different learning environments. I think mostly from intelligent tutoring systems, but developed in many places, not just CMU. So let's just go to public data sets. So actually, these public data sets, anyone can log in with. You can log in with your Andrew account. You can have access to these data sets. So if you want to do sort of any data mining with these data sets or exploring, it's free to use. That's why this resource is sort of here. And so let's just pick one data set here, just to look at what it gives you. So this data set has basically transaction level data from software. So it'll say every sort of thing the student did. Not necessarily where their mouse was moving, but basically any interaction that the student did with the system, any click they did. So it's pretty extensive data. So if we look at KC models. OK, so these are, for each data set, you can have a number of KC models. And these are basically your Q matrix, or your cognitive models. So here, there's some default model. This is for some fractions. like, so you see I have 1 digit, 2 digit, I don't know exactly what these mean, but we can sort of infer maybe. Add column, no carry, I don't know why there's a ton of these, but usually there's only one, I don't know. It's probably some sort of error. And then, and then there's different models. And then for each model, here they've sort of evaluated the model fit, and it'll sort of present you which is the best model. So this is basically a tool where you can sort of, let's say I have different potential theoretical models. I can sort of feed these models into, and you can actually, anyone can go and do this. You can export a model, add a new model to that, import it, and see how well it does. So if you have some sort of alternative theory, you can test it and say, okay, what if I treat my problems as having a different set of skills, or I modify the skills, and then see how well it does. So this is sort of a cool model, and you can actually view the learning curves here. It's a bit slow sometimes. Oh, this is really weird. OK, so this is not how a learning curve should look. So this is already telling you there's some problems here. OK, this is a more reasonable learning curve. So the red lines show you the actual data. So it's giving you, again, the x-axis is the number of opportunities. The y-axis here is error rate. So if the error rate is 100, that's bad. Error rate 0, that's good. And so we see that the red lines is showing the actual data. So each point in the red line is sort of a data point. Sorry, it's the average of the data points. So for each student, you look at opportunity 1 here, or opportunity 2, and you take the average of what the error rates was that opportunity. That's what the red curve is showing. The blue curve is showing actually this AFM model fit to the data. And so you see in these cases, at least, these ones that are marked good, you see that there's sort of good learning rates where they're decaying, sort of. This one's not that good. But this, I believe this is showing, this is showing sort of the aggregate. So if you average over all the knowledge components, and knowledge components are skills basically, you average over all the skills, this is what the learning curve looks like. So students are learning, and then they're not learning. Actually, they're forgetting, whatever. One thing to note, though, is that this is sort of a trend. Here it shows the number of observations. Can you see this? Here are these numbers. So it starts out, opportunity 1, there's 219 observations. That means there's 219 students. Again, 219 students. And then over time, the number of students who get that far drop off. So in the end, you have like only 11 students. Presumably, I don't know how this particular system was designed. This might be sort of like what's called a mastery learning system. So once a student masters the material, they're done. They don't have to do any more practice. So the students you have at this end are students who are still struggling. So that might be why you have this trend going here. And it's only like 11 students at the end. So just looking at the curve isn't necessarily fully informative. And can you actually do cool analyses? Like you can click on something and it'll tell you which problem. OK, it's not that useful here. But if you go on a particular skill, you can see like which problems it corresponds to. You can actually see what those problems are. You can see the different error rates of the problems. So this is a cool visualization tool. So you run these sort of models, and then you can sort of visualize to get a better understanding of what's going on. And this can be useful because you can actually use this here. So this shows, again, this shows us a number of skills for a particular data set. I think it's a geometry data set. And here we see that many of the curves have learning. I don't know why the blue lines aren't plotted here. I got this from another presentation. So many of these have learning, but you see that this particular skill doesn't have learning. So then you can sort of investigate why that's happening. And that gives you insight into which skills you might need to refine in your model. And this could have implications towards instruction. Because maybe you realize, you can either realize the skill is problematic, or the way you've defined the skills, or maybe you realize that your tutoring system isn't teaching that skill well. So then you can go back and improve your tutoring system. So this is sort of just giving you a small insight into how you can actually use these learning curves to sort of improve instruction later on. And another way that this is used, this could be used is, for example, you can actually model student learning in your system, and you can use that to see if a student's mastered a material. So maybe once a student gets to a low enough error threshold, you can move them on to, you can either tell them, OK, you've gotten enough practice, or you can move them on to the next skill. So maybe you want to keep practicing, having a student practice a skill until they reach below some sort of error threshold. So you can use this sort of model to make those kind of predictions. The actual model that's used in most of the tutoring systems, especially developed at Carnegie Mellon, isn't this AFM model. For some historical reasons, a different model is used. It's this Bayesian knowledge tracing model. So it's a model that, just briefly discussing it, that assumes students either know a skill or they don't. So in this model, you can think of the student knowledge sort of continuous, and it improves as the number of opportunities increases. In the Bayesian knowledge tracing model, you assume student knowledge is binary for each skill. Student either knows a skill or they don't. And you're trying to get a Bayesian estimate of what's their probability of knowing the skill. And once you reach beyond some threshold, like you're 95% confident they know the skill, then you've assumed they've mastered it. I don't know why they don't use this particular model usually to model student mastery. But for some historical reasons, that's just the way it's been done. And that Bayesian knowledge tracing model, again, was sort of motivated by the cognitive theories of John Anderson. He's one of the people who developed it. So it goes back to cognitive science, but I think for historical reasons, it's sort of stuck. So again, this goes back to how the work on cognitive science and AI was integrated at CMU, especially. And this has influenced lots of tutoring systems to this day, including the Carnegie Learning tutoring systems. OK, so now we're going to look at, I showed that potentially you can look at these curves and try to come up with a way to refine your cognitive model, right? I'm going to use cognitive model synonymously with Q matrix. But how would you be able to do this automatically? So that's the next topic we're going to look at. Are there any questions so far? OK. So we have this learning factors analysis. Again, this was a technique developed by the same set of researchers who developed the AFM model. So this is a method for automatically improving a cognitive model. As inputs, it takes a cognitive model, or a Q matrix, and it takes a model with hypothesized new set of skills, which is called a P matrix. I'm not exactly sure where these Q and P came from, but somebody thought these are good letters, so they've stuck. And of course, you get the student log data. So you basically get the number, the error rates, and whether a student got each question correct or not for each opportunity that the student had to practice. And your outputs are going to be cognitive models that fit the data best, along with the parameter estimates for those models, and the model fits. OK, so let's make this more concrete. First, let me explain what a P matrix is. So on the top here, we have the Q matrix you saw earlier, except that the mistake was fixed here. So we don't have division here, which is good. And here we have a P matrix. So a P matrix is going to give a new set of skills, hypothesized set of skills, that aren't yet in our Q matrix. So here, for example, we see multi-step. So this skill basically indicates whether you need multiple steps, multiple arithmetic steps to solve the problem. So the first one is 0, everything else is a 1, right? And then second, we see order of operations, which someone mentioned. So the only skill where order of operations sort of matters is the last skill, right? The only skill where you can make an error by doing not following the order of operations correctly is the last skill, because you can do C plus A before doing A times B. Do you have a question?
Couldn't you do in the second one, A plus C?
Yes, you could. OK, sorry. Again, I'm assuming you're doing it from left to right. So typically, students would. I think the only reason students would make this kind of mistake, as it's just a guess, is if they're learning over order of operations and they get confused about it. But typically, students are going to move things from left to right until they know otherwise. I think there might be some students who do that. So yes, it's not perfect, and you might add to your P matrix other types of errors that students might work on to differentiate. Good question. Any other questions about this? So your P matrix could have lots of potentially new hypothesized skills. And the way developing the P matrix is not, I don't know if, there might be AI techniques to do this, but this method that I'm talking about here, you need to have some sort of expert knowledge. So maybe you look at your learning curves and you get some hypothesized places where you might be modeling your skills incorrectly, and then you can add new skills to the P matrix to differentiate that. But this is not an automated technique, developing this P matrix. You give this as input to an algorithm that's now going to try to automatically improve your Q matrix. Does that make sense? OK, so how are we going to do this? So we're going to refine our Q matrix by adding or splitting skills. So what does that mean? So here I've shown that we might just add a skill from our P matrix. So this multi-step skill, maybe if we find enough evidence that it's a good skill, we'll just add it to our P matrix and we'll say, OK, that's also a skill. So these 3 skills here, they not only have an addition and a multiplication skill, but they also have this multi-step skill. Now, why would you want to model a multi-step skill? Potentially. I just added this randomly, but what's one reason you might want a multi-step skill? Maybe you wouldn't, but so because this, clearly if you think that this can just be decomposed into a multiplication step and an addition step, you wouldn't. But maybe you think once there's multiple skills, a student's going to struggle more with that problem, for example, just by the virtue of the fact that there's 2 skills that they have to do. Or maybe there's an integration step, for example. So that might be a reason. And maybe if you do want a multi-step skill, it might be different depending on what the skills are. So maybe a multi-step when you have a subtraction is different from multi-step when you have an addition, for example. So there could be lots of different hypothesized skills. And that has to either come from expert knowledge or from somehow looking at the data. And maybe there's machine learning ways of doing this, but we're not going to go over that today. OK, so that's adding a skill. So we're adding a skill from a P matrix directly to a Q matrix. What's splitting a skill? So here, we split the multiplication skill into multiply first or multiply second, where that split is done by basically taking the multiplication skill and combining it with the order of operations. Does that make sense? So here, before, all of these skills involve multiplication. But now, when we look at the order of operations skill, multiply first basically takes all of the cases where the order of operations was 0 and the multiplication was 1, and it assigns those a 1, and everything else is 0. And then multiply second does the opposite, sort of. It takes all of the skills where order of operations was 0 and assigns those a 0. And when order of operations and multiplication was a 1, it gives it a 1. Does that make sense? So we sort of split the multiplication into 2 branches, saying that the skill might vary depending on whether order of operations matters, again, if you're doing things left to right, or doesn't. Does that make sense? So if we have a number of skills in our P matrix, we can either add those skills directly, or we can split an existing skill in our Q matrix into two branches. And then we can repeat. So maybe a single skill might get split 4 times if we take 2 different skills from a P matrix and split on that. Does that make sense? OK. So now let's see how we can automatically sort of, yeah.
Yeah, it doesn't make sense. Like, how you know which skill you split and according to which skill in P matrix? Like,
how do you know? Yeah.
I mean, how you split, for example, based on multi-step P matrix skill?
Yeah.
Or like why you split multiplication but not addition, etc. I mean,
yeah.
I mean, like the example that you showed makes sense.
Yeah.
There is
how is the general?
Examples that does not make sense at all.
So do you mean does not make sense how you would do it, or does it make sense why you would do it, or like?
Yeah, why you would do
yeah. So I'm going to go into the why. So basically, how do you determine which ones to split and which ones to add? Is that your question? Or because some of them might not make much sense. I mean, you can do it. You can split according to multi-step. You basically just sort of take the joint between multi-step and like the inverse and flipping multi-step with any of these columns. But you might not want to do that. That might not make much sense, is what you're saying, right? Yeah. So how do we know what makes sense? Yeah. So we're going to try to infer that automatically. You could use domain knowledge. So again, a person could do that. But we're going to discuss just the simple sort of method of doing this using search. That's what I'm going to talk about next. So the method LFA, you're going to start with your original Q matrix. So this is some Q matrix that you, as an expert, have developed. And then you're going to apply all possible add and split operations using the P matrix. All possible one-step add and split operations. So some of them might not make sense to you, but the method's going to do it. So you're going to apply, for example, this multi-step. You're going to split according to each of these, or you add it. Yeah. So the number of operations, I guess, would be quadratic. Maybe you don't do all of them, but it would be quadratic, I guess, in how many, or not quadratic, but it'd be the number of things in your P matrix times the number of things in your Q matrix, right? Plus 1 for each thing in your P matrix, because for each add operation. Well, let's just assume you do all of them for now, even though it's a lot. OK, so you do that, and this is going to be a search algorithm, right? So we're going to evaluate the model fit for each of these new models, and then we'll add these onto our frontier. So I'm going way back to when we talk about search. So hopefully you remember some things about that. So then we remove the model from the frontier with the best fit so far, and make that the new Q matrix. And then we just repeat. That make sense? So it's a simple sort of search algorithm. Again, we're going to do every add and split operation we can. And then one step, again, add or split operation. We're going to evaluate how well each of those models do. We add them all to our frontier, and then we pick sort of the best fitting model so far that's still in our frontier. And then we make that our new Q matrix, and then we repeat. And at the end of this process, we're going to find what's the best model. So now the question is, what is the goal node here? Because if we're doing a search algorithm, we're searching for something. What are we searching for? Well, intuitively, what are we searching for? Yeah, the best fitting model. But do we know what that is? That's the problem, right? So when do we stop?
Probably stop in the like one of the local maximums.
Did
Like
you stop when you exhaust your frontier?
But you might keep adding things, right? Because the number of, if your P matrix is large, you potentially have like exponentially many nodes. So you might just keep adding things to your frontier. So I guess the heuristic is you just stop after a certain number of iterations. And then you choose the best fitting model you have so far. Does that make sense? I mean, there's no way to, I mean, it would take too long to go. So this is sort of a way to sort of inform your search to try to find a good model. And then, with some limited amount of computational resources. So at some point you just stop and then you just output the best fitting model, or you can output sort of the top fitting models. And then a human can look at those and see which makes the most sense. Maybe you have like 3 or 4 models that have similar fits, but maybe like theoretically only 1 or 2 of them make sense. And then you can go with this, yeah.
But after each step, you delete almost from frontier and kind of start from scratch, correct? Like you do not accumulate your frontier.
You do.
Then why do you want to accumulate that? Because you already picked the best Q matrix, so then all other models.
Good question. We'll get back to that.
Okay,
Yeah, good question. Okay, so one question is, first of all, just sort of a divergence, but related, is how do we evaluate model fit? So one thing we could use is log likelihood. So is that a good way to evaluate a model's fit? Yeah? See some nods. How many people think it's a good idea? 2. How many people don't think it's a good idea? How many people are left? Okay, most people. Okay, but there's even more people left. But okay, that's fine. So log likelihood has some problems because imagine as our matrix gets larger and larger, we might be able to get a better fit, right? But we have more parameters. So we want to avoid overfitting. So there's different ways of doing that. I don't think this was covered in the class, but these are this general class of techniques called like minimum description length. So there's I don't know how you pronounce it, but Akaike information criterion, typically pronounced AIC. So basically, this is just a model. Sorry, not a model. You take the 2 times the number of parameters, k, minus 2 times the log likelihood. And that's how you evaluate the model. So basically, it trades off between model complexity, measured in here, 2 times k, and model fit, the log likelihood. You're shaking your head.
Why is it 2? Yeah.
Oh yeah, why is it 2? I don't know. There's some reason. Yeah, that might be the case. Derivative.
Oh, sure. Okay.
Yeah.
Yeah, exactly.
And the log likelihood is going to be, well, so do you want to take a smaller AIC? Like, is a smaller AIC model better or a larger AIC model? So, I mean, there's 2 ways to figure out the answer. One is more parameters better or less parameters? And one is a smaller log likelihood better or greater? So a greater log likelihood is better, but it's negative, so a smaller AIC is better. And furthermore, having less parameters is better, so a smaller AIC. Yeah, so a smaller AIC is better. Another alternative is to use Bayesian information criterion, where instead of 2 times the number of parameters, you take n times the number of parameters, where n is the number of observations that you have. So this is basically a much more conservative sort of, it's punishing more parameters much more than AIC. And I think both of these are used in practice. I guess I'm not sure what the rule of thumb is for which one you want to use when. Different people have, pick different ones. And what's another way we can evaluate model fit that we've learned about? Basically, what's another way sort of to evaluate model fit where we take into account overfitting? We want to sort of avoid overfitting. Yeah?
We had normalization.
Regularization?
Yeah.
So that's something you can do. Yes, that's something you can do. But let's say we don't do that. How do we evaluate a model? So we're just looking at metrics for evaluating a model. Let's say we didn't add any regularization. But that is something you could do. Sorry? OK, yeah. So split your data into test and train set, or more generally cross-validation, right? So this just in particular, you can use like cross-validated root mean squared error. You can replace this with any error metric. But this is sort of one typical choice, which is, so you basically, and you can do any number of folds. You can do any version of cross-validation. But that's one way to do this. And this is sort of ideal to do this, but it takes a lot longer to compute, right? Because you're splitting your data set into many sub-data sets. And so you have to run the model fit on each of those. So this takes a lot longer than AIC or BIC. AIC and BIC, you just fit the model once, and you just sort of correct for it using just one equation. So it's much quicker. So it just depends on how much computational power you have, which you choose. And actually, there's interesting results where at least AIC, I think, asymptotically, it's equivalent to, I think, leave one out cross-validation for a linear regression model. So in a particular case, but it's a pretty interesting result that says asymptotically they're related, at least in some sense, which is pretty cool. OK, any questions about this part? OK, so we can choose any of these to evaluate our model fit. And each of these sort of somehow account for model complexity. So more complex models will be penalized in some way. OK, so here's an example. This is from the paper that did this. So here we're using BIC as the metric. So we start with the original model, the original Q matrix. It has a BIC of 4,328. And then here it just shows a number of different splits. There's 50 more, I guess, that they didn't show. And then, so which of these would be picked first? Which of these would be popped from the frontier first? What? The left ones, yeah, because it has the smallest BIC. So we go here, and then for everything else in the frontier, we're going to add the one with the least BIC. Which one will be next, assuming it's none of these that aren't shown?
Third one from the left.
Right, so this one. We do this one, and then we go here. So we can go back and forth. It's not necessarily going in a single branch. Does that make sense? OK. So now let's ask a question, a poll question. So the question is, LFA implements which of the following search algorithms? So here are a few search algorithms that you've learned. Oh, I think it's missing one, maybe. But uniform cost search, greedy search, or greedy best first search, A-star search, none of the above, or beats me. I think there's one more choice. Oops. Yeah, also theta star that I forgot to put there. OK. So hopefully you remember what these algorithms are, or at least you remember which one's the right answer. And if not, if you're quick enough, you can go back to the slides from the first search lecture. OK, interesting. We have everything but none of the above. OK, so who wants to say why it's greedy best first search? Or who wants to advocate for that? Let's go back to here. Nobody? Anybody?
Not when you put it like that.
What?
I said not when you put it like that.
Well, let's see. It might be. Let's see. Yeah.
I don't think it's greedy, because if it was greedy, you'd go down one branch, stay in it, and just search the lead of that particular branch. And we're not doing that. So.
Right. So, yeah. So one thing to notice here is that we've already found a better model, and then we go to a worse one. This is sort of the point you were raising earlier, I think. That what's going on here? Which search algorithm actually does that? So, OK, first of all, you can probably think of these BICs as sort of a heuristic, right? It's sort of a heuristic distance. There's some optimal BIC. That's the goal. And this is sort of a heuristic measure to the goal, right? But even once we found something better, first of all, some of the leaves have so it might be that all of the leaves, for example, are worse, like have a further distance to the goal. OK, actually, the first thing to notice here is that we might not be able to reach the goal from a certain node, right? So we might have found a best node, but that goal might not reach the best model, right? So it's already problematic. So we know it can't be A-star search. It also can't be, actually, it can't be any of the search algorithms. This is very different from things we've already seen, right? Does that make sense? So it's possible, we can never reach the goal from the best model that we found so far. So that could be a local optimum, basically. Sort of different from search algorithms we've seen so far. And furthermore, we're going to explore algorithms. We're going to explore models that are worse than what we've already branched off of. So it's also not greedy best first search. So it's actually none of the above. which nobody thought it was, which is interesting. So the authors actually, in one paper they advocated this as A star, in another paper they said it's best for search. So you guys aren't, I don't blame you guys, but when I was thinking about this, I was like, this is really, it's more heuristic than our heuristic search algorithms in some sense, because there's no real guarantees here. You're just trying to find a good model, and this is a search algorithm that helps you do that. But there's definitely like local optima here, if that makes sense. And maybe those local optima are good enough, because you're not even branching out all the way to find the goal. So maybe the best model we'll ever find is, for example, this one. Although in this case, it seems like after 15 expansions, it was this model here. Does that make sense? Any questions about that? Yeah.
It's still, I mean, this model is definitely not what you want to do intuitively.
OK, why not?
Because if I found already some matrix that is good enough,
Yeah.
it couldn't be the case, or like almost every time the best model that I'm looking for is under this branch. Just because like you can think intuitively, if you already split some of your skills,
Yes.
and then the best model, let's say, split some other skills, okay? Then you can just add those splitting skills to your model that you currently have, and you will be in a good shape. Because splitting the skill will not make your model worse. It will just stay at the same spot. Because you know, like taking addition or splitting the addition is the same. That's why
So
you can just branch better. So I mean,
I'm not sure if that's true, because yeah, I'll have to think about that, because there's a complex sort of interaction between skills. Like,
oh, I mean,
there's multiple skills per item. Sorry, what?
Like,
What?
You can put beta to that skill just being 0 and here we go.
But you wouldn't fit. Oh, okay. Yeah. That's what you're. But you're penalizing more parameters. Actually, that addresses the question you're answering, right? The BIC especially is going to penalize more parameters.
Okay, maybe.
Yeah, which makes sense, because yeah, you can add everything to your Q matrix. You can have a huge exponentially large Q matrix, but that's not going to be the best model. That makes sense?
Maybe you want to jump to a worst case with some like probability or something like that, but like going in this order definitely doesn't.
Okay, well think about an alternative, and if you have one, that could be a research paper. I don't know of any, there might be further improvements upon this model. It's I guess one point is it's a very simple model, and I guess we should wrap up. But I don't know of any alternatives that have been proposed to this particular approach. Yeah, here's just a summary slide. So I guess next time we'll continue with assessment. So we're going to talk about applications to assessment. So thanks a lot.